Section 5 of the workshop is where you'll get familiar with interrupts and the timer. You will use the timer to generate interrupts to the main routine. If you're not already familiar with the concept of microcontroller interrupts, now would be a good time to go out on the web and look that up. Some of the features available on the Timer A2 and Timer A3, they are a asynchronous 16-bit timer counter. They offer a series of different modes, continuous, where the timer continuously counts up to FFFF and then rolls over to 0. In most cases like that, it'll generate an interrupt at the rollover. That has limited. That's a limited help to you, as the amount of time that it takes to run that isn't very selectable. Now, in the up mode that's shown there in the lower left, the timer counts between 0 and the value in the capture compare register 0. So you can pick the time that the interrupts are going to, at which the interrupts are going to occur. If you want to do things like pulse width modulation, an up-down counter is very useful. So you can set the mode as an up-down counter and have the timer count between 0, the value in the capture compare register 0, and 0 go up, down, up, down, up, down. The difference, like I've said earlier, between the Timer A2 and Timer A3, the Timer A2 offers 2 CCR, capture compare register, and the Timer A3 offers 3. Now, both of these timers are capable of doing simple PWM. If you need to drive an LED, change the brightness of an LED, if you want to drive a servo motor or something like that, that's very straightforward to do with this timer. And if you look in the code examples available on the TI MSP430 website, you'll find code that does exactly that. There are 2 or more interrupt vectors for fast decoding on these timers. Also bear in mind that some of the parts not only have 1 timer, but they have 2 timers, so you can get multiple interrupts on this. So when a peripheral or a programmed pin or something else, when it creates an interrupt, we need to understand how the interrupts in the stack operate together. When an interrupt happens, any currently executing instruction gets completed. The program counter, which should be pointing to the next instruction, gets pushed onto the stack, as we can see in the diagram on the bottom down there, bottom right. Then the status register gets pushed onto the stack. You can see TOS says the top of stack down there. Then the interrupt with the highest priority is selected. There is no preemption in the interrupt controller of the MSP430. If you have multiple interrupts, pending, the interrupt with the highest priority gets selected and will be run. So the interrupt service, or rather the interrupt request flag for that interrupt that went off, gets reset automatically on those flags that are a single source. Something like the counter compare or capture compare register 0 for the timer. That's a single source flag. There are multiple source flags. For instance, the GPIO, where we have an interrupt for the entire port, not for every single pin. So when you get that, you have to go in there, and once you get the interrupt, you have to do a little interrupt handler that goes and finds out exactly which one was done. So for multiple source flags, you don't want to reset them automatically. Those have to remain set for your interrupt handler. Then you can service them by software. So once that's done, the status register gets cleared. That means any low power mode gets terminated. We're back to active state. Also, the global interrupt enable bit gets cleared, so that will disable any further interrupts. That's a good thing. It's one of the first rules of microcontroller processing or microcontroller programming is that you don't make nestable interrupts. Of course, that's also the first rule that's broken, that people make interrupts nestable. But that means you have to take a lot of care to do that. We'll talk more about that later. The content of the interrupt vector gets loaded into the program counter. Those interrupt vectors, remember, are up there at the top of flash memory. That tells us the location of our interrupt service routine. So now the program will continue execution at the interrupt service routine that's loaded at the address that was in the vector table. The G2553 vector table looks like this. Starting up at the top at FFFE, in order to program that in. That's FFFE and FFFF. You'll see that the reset interrupt is there. The power up, the external reset, the watchdog timer, a flash violation, the PC out of range will all generate a system reset interrupt. That is at 31, the very highest priority on the device. Just below that is the non-maskable interrupt. That could also be oscillator faults, flash memory access violations would all generate a non-maskable interrupt. Of course, the reset and the NMI are the only non-maskable interrupts in the system. You don't want to be able to mask those out, and they're both the highest priority. Coming after that, you'll see we have timer 1, interrupts for the CCR0, CCR2, and some of the other registers inside the timer. Next is a single interrupt for the comparator. The interrupt for the watchdog timer is after that. 2 interrupts for the timer 0, A3, CCR0, CCR1, and some of the other registers. The next 2 interrupts are for the USCI, the Universal Serial Communications Interface, as shown. The one below that is the ADC10 interrupt. Just below that, you'll see the I/O port P2 and then I/O port P1. Now, some of these interrupts have more than one source. Something like an I/O port, for example, have as many as 8 sources. So when you take an interrupt and the interrupt is processed, that interrupt flag will not be automatically cleared for you. You need to go back and clear it after you take a look to find out exactly which pin gave you an interrupt. Something like the watchdog timer, the comparator, the ADC, those things have a single interrupt source, and the interrupt flags will be automatically cleared for you. So once the processor is interrupted and the interrupt mechanism has loaded the address of the interrupt service routine to be executed into the program counter, we're going to jump off and do the interrupt service routine. Here's an example of an interrupt service routine right here that we might write in our code. So you can see we've used this thing called a pragma. This pound pragma up at the top identifies this function as the interrupt service routine for the listed vector, WDT under vector. If you go back to the previous slide, you'll see that the watchdog timer vector is at that exact address. This identifies the following function as being the interrupt service routine that's going to be for that vector when it's called. So then we need to give it with this interrupt void, we need to identify what the ISR name is. That will give it an address, that this location identified by WDT under ISR, that address is going to be plugged in automatically by the compiler to the watchdog timer vector. That way, when the interrupt service routine gets run, it will jump right to the first one of these instructions, run all of these, and then jump back into code. No special return is required. Nothing else is required to do to make an interrupt run. And we're going to see all this in the lab. Lab 5 will use the 16-bit timer running on the A clock, sourced by the VLO, to generate a delay. When the timer reaches the end of that delay, it will generate an interrupt. The interrupt hardware on the MSP430 will find the correct address of the interrupt service routine that you've written and go ahead and run it. These are all real-world skills that you need over and over when working with the MSP430. In step 1, create a new project by clicking File, New, CCS Project. Again, we'll make the selections as shown in the drawing below. If you're using the G2231, make sure you make the choices for that part. Make sure you click Empty Project at the bottom, and then click Finish. The solution file that we had from the last exercise will be used as a starting point for this lab exercise. We went ahead and cleaned the file up a little bit to make it more readable by putting the initialization code into individual functions. So open the lab5 under start.txt file using file open file. That should be in your lab5 file folder. When that opens up, copy all of the code in lab5 under start.txt and paste it into main, making sure that you erase all the existing code in main.c. This is going to be the starting point for this lab exercise. In step 3, go ahead and close the lab5 start file. We don't need that anymore. So go ahead and run the code. And if everything's working right, the green LED should be blinking about once per second, and it should function exactly the same as the previous lab exercise. When you're done, halt the code and click the Terminate button to return to the editing perspective. Now we want to use the timer to implement that delay. In the next few steps, we're going to implement the 1-second timer that was previously implemented using the delay intrinsic with the timer. So go ahead and find the delay cycles 125,000 and delete that line of code. In step 6, we need to add a function to configure the timer. So add a declaration for this new function to the top of the code underneath the one that already exists for config ADC10. And that should look like void config timer A2 void. Now, actually the timer on the 2553 is the timer A3, but that makes no difference for what we're trying to do here. When you've done that, add a call to the function underneath the call to config ADC10 that says config timer A2 with no parameters. And then we want to add a template for this function to the very bottom of your program. So there's a void config timer A2 void. We're not passing any parameters back and forth, with an open and closing brace. So that takes us to step 7. So we need to populate that config timer A2 initialization function with the code to configure the timer. We could take this from the example code, but it's pretty simple to do. So let's do it ourselves and take a look at how it works. Add the following code as the first line. This is cctl0 equals ccie. That's going to enable the counter compare register 0 interrupt in the cctl0 capture compare control register. Unlike the previous labs, this one's going to be using interrupts. After that, add the next 2 lines. CCR0 equals 12,000, and then timer A control equals timer A select 1 and MC2. We'd like to set up the timer to operate in continuous counting mode, sourced by the A clock, and generate an interrupt every second. Reference the user's guide and the header files and notice the following, that TACTL, that's the timer A control register, the TASSEL1, that selects the A clock as the input, and MC2 sets the operation for continuous mode. When the timer reaches the value in CCR0, the capture compare register 0, an interrupt will be generated. Since the A clock is running at 12 kilohertz, the value in there needs to be 12,000 cycles if we want it to go off every second. In step 8, we've enabled the CCR0 interrupt, but global interrupts need to be turned on in order for the CPU to recognize that individual interrupt. Right before the while loop in main, add the following. Under BIS, under SR, GIE. GIE is global interrupt enable. So now we have the timer enabled, interrupts enabled. Now we're going to need to have an interrupt service routine that can actually run. So we've got them set up. We need to create this interrupt service routine that runs when the timer interrupt fires. Add the following code template to the very bottom of main.c. This is a piece of code. These lines of code identify this as the timer ISR code and allow the compiler to insert the address at the start of this code, that's timer A, into the interrupt vector table at the correct location. That's timer 0 under A0 under vector. So the purpose of these two pieces of code is to take the address timer A and plug it into the correct place in the vector table. Look it up in the C compiler user's guide. This user's guide was downloaded in Lab 1. So in step 10, remove all the code from inside your while loop in main and paste it into the ISR template. This will leave the while loop empty for the moment. So almost everything's in place for the first interrupt to occur. In order for the second, third, fourth, and so on to occur at 1 second intervals, two things need to happen. The interrupt flag has to be cleared. Well, that's automatic. The CCR 0 has to be set 12,000 cycles into the future. So add the following as the last line in the interrupt service routine. CCR 0 plus equals 12,000. In step 12, we need to have some code running in order to be interrupted. In reality, we don't. You could have a while loop sitting there with nothing in it that would run, but I think it would be more interesting to actually have something running. So what we're going to do is add a little while loop with some blinking LEDs. So take the 4 lines of code shown in step 12 and paste them into your while loop. This routine doesn't use any intrinsics, so when we're debugging the interrupts, they'll look good in C rather than dropping you back and forth between assembly. Oh, and don't forget to declare I at the top of main.c, volatile unsigned int I. As we progress through the labs, what we're trying to do is take you a bit further away from using hex codes and a bit more into using codes that are much more readable. So let's make some changes to the code for readability and for the LED function. Take a look in your fault routine and you'll see P1 out equals 0x1. We can change that to P1 out equals bit 0. That's easier to read. In the config LEDs function, you'll see P1 dir, that's the direction register, equals 0x41. Let's change that to P1 dir equals bit 6 and bit 0. In the timer ISR, you'll see P1 out equals 0x40. Let's change that to P1 out or bit 6. Finally, find P1 out equals 0 and change that to P1 out and equals the not of bit 6. At this point, your code should look like the code that you'll see on the next 2 pages of the workbook. We added the comments to make it easier to read and understand. Go ahead and click the Save on the menu bar to save the file. And we'll go ahead and page slowly through the code. Let's go back up to the top and we'll see the very top of the code. Give you a chance to look at that. And then we'll click down one. Give you a chance to look at that. You should note that for reference, you can find this code in the lab 5 under finish.txt file in the files folder. So in step 15, click the debug button. The CCS debug view should open, the program load automatically, and you should now be at the start of main. Go ahead and run the code and observe the LEDs. If everything's working correctly, the red LED, that's what's in the while loop, should be blinking about twice per second. This is the while loop that the timer's interrupting. The green LED should be blinking about once per second. This is the rate that we're sampling the temperature sensor. And looking at the board, that looks pretty good. Go ahead and click Suspend to stop the code. In step 17, make sure that the temp raw variable is still up there in the expressions window. If not, you can double-click temp raw in the code like we did before. If needed, click on the expressions tab so you can see the variable in the watch window up there. So in step 18, in the timer A2 ISR, find the line with P1 out and equals the knot of B6 and place a breakpoint there. Right-click on the breakpoint symbol and select Breakpoint Properties or Breakpoint. There we go. Again, we're still having some difficulties with our capture system, so make sure you change the breakpoint property action from stop to refresh all windows as shown in step 18. Go ahead, say OK. Go ahead and run the code. The debug window should quickly stop at the breakpoint and the temp raw value will be updated. Observe the watch window and test the temperature sensor as you did in the previous lab exercise. I'm going to put my finger on there and hopefully the temperature will go up as it did before, and it does. Terminate your active debug session using the Terminate button. Close the debugger, return to the Edit view. In step 21, close your project by right-clicking on Lab 5 in the Project Explorer pane and select Close Project.